Hey, PStat. So we're going to jump into section 2.2, looking at density curves and normal distributions. That is a big one. So by the end of this section, you should be able to use a density curve to model distributions of quantitative data. So a normal distribution is a type of density curve, so we've got to start with that definition. Identify the relative locations of the mean and median of a distribution from a density curve. Take a peek at that. And then we're going to get into a lot of normal calculations here. We're going to use the 68 to 95 99.7 rule. Some of you may have experience with that to calculate values, proportional values in an interval, and maybe find corresponding values corresponding to a percentile. And then basically using table A. We're going to use a table-based version. You could use calculus, but we're not going to, this is not a calculus-based statistics, to calculate some of those things within a normal distribution, and then finally assess whether a data set follows a normal distribution. All right, so in chapter 1, we developed a kit of graphical and numerical tools for describing distributions. Now we'll add one more step to that strategy. So we had graphs. We always plotted our data. If we had quantitative data, we'd make a graph, usually a dot plot, stem plot, or histogram to kind of just get a visual of that. We'd look for the overall shape, overall pattern, shape, center, and spread or variability, and for striking departures such as outliers, and that'd be kind of help us analyze our data. And then we calculate some numerical summaries like mean, standard deviation, median, IQR to do that. So we're going to add one more step to this. When there's a regular overall pattern, we can use a simplified model called a density curve to describe it. So certain data sets, we'll kind of jump ahead here. Maybe it looks like it follows this really nice bell-shaped curve that, and we'll be able to assess, is that a particular curve that it's fitting, and like the normal curve. And so we'll look at what that curve is in a little bit and see if a data set does fit that normal distribution that we see pop up so much in different things that we study. All right, so a density curve is a curve so it's always on or above the horizontal axis. So it's a curve that stays above the axis, and the area below it is exactly 1. And so it actually kind of shows a proportional relationship, so that the entire area is 1, and so a section of it will represent a certain proportion of that distribution. And the area under the curve and above any interval of values on the horizontal axis estimates the proportion of all observations that fall in that interval. So because we have that area of 1, if about half of it sits in a particular region, that should be about half the distribution. If a third of that area is above another interval, those values should happen about a third of the time. All right, so here is an example of some journeys, and we have a kind of almost a flat-ish looking distribution that kind of peaks up here at a few points. But it seems like this journey time apparently always kind of ranges from 2 to 5 minutes. And so what we can do is we can kind of estimate, rather than count up all those dots and figure out what proportion of the time we're in one region or the other, maybe we can fit a density curve to this. And so we can take this, we have this very basic density curve here. It's actually not curving at all. It's a straight line, but this shows kind of a uniform distribution. And we're modeling this shape. It's not exactly this over here, but it generally fits that same shape. And so we can model that distribution. And so this density curve, notice that it goes from 2 to 5. It would actually have a height of 1/3. So this length here for this rectangle that kind of is being formed is 3. That height is 1/3. So this entire area is 1. And so we can fit that. So the overall pattern of this dot plot of the amount of time it has taken Selena to get to the bookstore by train each day for the last 1,000 days can be described by that horizontal line. So it's not exactly that. There's some other variability here, but we can kind of fit that overall pattern with that. We can do something similar for other shapes. So the overall pattern of this histogram of scores for the 974 7th grade students in Gary, Indiana, on the vocabulary part of the Iowa Test of Basic Skills can be described by a smooth curve drawn through the tops of the bars. So we kind of fit that data in here. We're seeing, that is kind of that bell-shaped curve, maybe even that elusive normal distribution that we're talking about. So we had kind of a uniform one. Here's a nice bell-shaped one, and it can be all kinds of shapes and so on when we try and kind of fit a model fit a curve to our data. It's kind of almost like a line of best fit for a scatter plot. It's a curve that fits like our histogram or our dot plots. We kind of ignore the little mini variations and just get that overall trend, and we can use that to describe distributions. All right, so the mean of a density curve is the point at which the curve would balance if made of solid material, and the median is the equal areas point. So in a symmetric distribution, kind of a bell-shaped distribution, the mean and the median would both be right under the center, about the same. But if we have a skewed distribution, actually you've already seen me draw shapes like this on the board. I haven't told you they're called density curves, but those are density curves. So there I kind of draw a general shape just with this line. So this right tail pulls the mean further to the right than the median. We kind of already had this concept. So the mean will be above the median, and that's kind of this showing within a distribution the relative position. The mean would be the balancing point. If I was going to try and balance this shape here on top of something, where would that fulcrum be, that balance point? And so it looks like the mean would be right there. The median is the equal areas. Where would we have equal area to the left and the equal area to the right of it? So the mean and median are the same for a symmetric density curve. They both lie at the center. The mean is if it's pulled in the direction of the skew. Describing density curves, a density curve is an idealized description of a distribution of data. So it's just that ideal curve for that data. We distinguish between the mean and standard deviation of the density curve and the mean and standard deviation computed from the actual distribution. So the mean and standard deviation of a density curve will have models for that, especially once we get to this normal distribution versus our raw data. And the usual notation for the mean of a density curve, now that we're getting into kind of a theoretical, it's not based on a sample, we actually use a different symbol for the mean. We're going to bring in this symbol here. It kind of looks like a U with a little, like, I don't know, thing hanging off the front of it, a little like loop in or whatever. So that is the Greek letter mu. And that's going to represent the mean of a density curve. So we're kind of getting a little more theoretical. That's also the same symbol we actually use for a population mean. So it's not X bar. X bar is for the actual data, the raw data. This is a little more theoretical, the mean. And then the standard deviation symbol, we switch over to sigma, and you guys have seen that in the calculator. This lowercase sigma is the standard deviation, and that's what we use, and that's getting kind of towards that theoretical. We use those symbols for the more kind of ideal theoretical values we have in these density curves. Also for we use those symbols for populations, because we kind of have those theoretical population mean and standard deviation that we would like to know about, but in reality we usually can't figure out exactly what they are without testing everybody. All right, so that is the basics of density curves. We'll get into normal distributions in the next one.